So today I wanted to show a project I've been working on for about 2 years now. It is still in very much sort of a draft phase, in a throwaway phase, but regardless. So the project is called Wirewright. And what Wirewright is it is so-called rewrite environment for self-embodied programs. So what are self-embodied programs? What is a rewrite environment? And so on. So, I mean, these are hard questions, and I won't be able to answer them in this particular video, but in this video I wanted to just demonstrate the basics of what is possible and impossible in Wirewright right now at the current stage of development. So I think it's quite important sort of to show this. So Wirewright attempts to remove the interpretation or compilation process entirely. So in Wirewright we do not have compilation or interpretation, so it is not a traditional sort of programming language. But you know, if I wanted to sort of explain really quickly what Wirewright is, I would say that it is something between a programming language, or rather an environment like Smalltalk, for instance. So it's not just a language, it's an environment. Okay. One other thing it can be compared to, Wirewright, I mean, is a game. So we, like in games, we have a loop, and we can exercise this loop very easily. So you can see that we are running a sort of game loop here that is allowing us to update things very nicely. I mean, it's just one aspect of that comparison between Wirewright and a game, but sure. So we have like a game-like loop, main loop. So the third thing that it can be compared with is a cellular automaton out of all things. A cellular automaton. So that's that, right? So something between these three things is what Wirewright is. So let me just show again what's possible right now, and the hello world of Wirewright is a counter. Now let me use these fancy things because terminals apparently do not support some keys. So the simplest thing that you can do that is sort of showing the interactiveness and the rapid development sort of speed pace, I don't know, in Wirewright is definitely a counter example, like they do, you know, those React web development kind of counters. Let's try to build something like that in Wirewright. Again, this is going to be pretty sort of bare bones because right now we do not have a lot of utilities, a lot of styles. We are running inside of a terminal out of all things, so we do not have access to font sizes, for instance, and the various sort of positioning techniques and so on. Like, we can do certain things, but the moment you want to get sort of stylish, the terminal sort of falls off. So, but regardless, like, just to show the progress of like what is going on this small example. Now, I'm not going to be able to explain a lot because there's a lot of sort of ideas and thought. Again, it's about 2 years of sort of ideas and exploration, so there's a lot going on here, and unfortunately I just don't have the time to explain so succinctly what is going on. I'm going to try to, but again, I may fail, and maybe repetition will help. So with more and more examples, with more and more sort of interesting playings, we will be able to understand what is going on and sort of use that to our advantage. So let's just take a look at Wirewright then, and in fact, what you're looking at right now is something called usoma or musoma, and it is again, I compare musoma to a browser. Like, we have the internet, and then we have browsers that allow us to view this internet thing and to browse the internet. Similarly, musoma is a tool, a graphical user interface program that sort of allows users to interact with Wirewright, which is a variety of systems. And musoma is like an interface to all those systems. So let's like a graphical user interface. So let's just try to implement a counter. So the first thing you can see, we have hints. Now this is a Lisp or like S expression inspired sort of syntax. So you have to understand that this is not a programming language. What you're seeing right here is a structured editor. And I mean, I'm not going to digress too much into this direction or in this direction, right? But this is a structured editor, and the underlying data structures, they are not necessarily like concells or like whatever Lisp is doing there. We are just using like Lisp S expressions or something along those lines to pretty print the underlying data structures. So the underlying data structures are called terms. Okay, terms. And there are various ways of pretty printing them, and as you can see, one of those ways is to pretty print the following term. We have a list, or like it's called a dictionary. In this case it's called an items only dictionary because we only have items. And so we pretty print this dictionary. So this is sort of one layer of pretty printing where we have like the contents of the items only dictionary. But when I leave the cursor, or with the cursor, you can see that it pretty prints differently. It pretty prints as like these double colon thingy with a syntax highlighting and so on. So this is also pretty printing, so that this has nothing to do with the underlying data structure. The underlying data structure is this. And even this is just a pretty printed version of the underlying data structure, which is again a dictionary in this case. So again, as I have said, there are three main kinds of dictionaries. There are items only dictionaries. For example, this comment here is an items only dictionary. We can add a pair, so like we can do like, I don't know, foo 100. And this is a pair that we have added onto this comment, and now this comment won't be pretty printed if I leave it, because so this is the task of usoma, to sort of pretty print these things, and in this case it doesn't know what to do with this, so it doesn't match the comment pattern because we have this extra foo key or pair in this case. So what you're looking at here is a dictionary that has both items and pairs. So if you notice, if I remove the items part, we would get different formatting with these curly braces and so on. Now you can note that the cursor exists within this world, and this is why I've compared Wirewright to a game. So you should imagine that the cursor here is the player character that you are controlling. So when you send your keys to this player character can navigate this abstract world, and sort of in this case you can edit this abstract world using the cursor. So when I'm typing like that, I'm actually sending signals to this player character, the cursor, and this cursor is able to enter stuff. Like, this is just a very basic, crude, I should say, explanation of what is going on. So let me use the fancy shorthand. Of course it doesn't work. Don't remember why though. I think it failed somewhere. Yeah, so I mean, we can just remove the key here and that would solve the issue. So again, let's just get back and implement implement the counter example. So we have what is a counter? Well, I mean, from a user's perspective, it is a button of some kind. So you can see we got this button hint. Again, there are hints for the available nodes, so you can sort of navigate through these hints and learn more. Now we have a button, and now you can see we've got a more sort of expansive hint which shows the variants of a button, and in this case there are 2 variants for now again, and it describes the sort of parameters or arguments to the button. Yes, again, I'm not able to sort of talk for hours here, so let's just get going. So what does a counter have? A counter has a button that increments the counter. Let's type increment. You can see we have advanced. There are still 2 variants available because, you know, that's the thing. And of course, each of those variants, you know, presents a different way of implementing the counter, but we're going to go canonical here, so I'm going to use the as variant. So I mean, I guess, so it's nice with Wirewright because it is very, very playful, and it sort of it lets you experiment. So, you know, like, instead of trying to explain what the as variant does versus the sort of variant without as, let's just use another node. So first of all, let's just instantiate this first thing, just so that we can show it. So a button needs, again, I'm trying to find a useful analogy here. Let's say a button needs a channel where it would shout something when it is clicked. So in this case, this particular variant of a button will shout increment. So it will shout its own caption to this channel, quote unquote. Now, in fact, these are not called channels; these are called edges. And if you know, we are being extremely precise, these are hyper edges. But again, you know, for the sake of an analogy that helps to understand this a little bit better, let's call these channels for now. So, you know, a button has a channel, or accepts a channel, where it will shout something when it is clicked, and in this case it will shout increment. Let's call this channel, I don't know, actions. Now the button also needs a mailbox. So a mailbox is a dictionary, an empty dictionary in this case, that will be used by Soma, the graphical user interface, so to speak, to communicate with button, the node. So these things, for instance, this button is called a node, and Soma is rendering this node, so it's creating all sorts of intermediate trees, it's positioning, it's doing layout, and so on and so forth. In the end, you see on the screen, let me just add a mailbox. In the end, you see on the screen a button, and Soma needs to communicate with the button, the node, when you, for instance, click. So when I click this button, Soma briefly communicates with this button by sending a press signal to here, and you know, this way the button actually knows that it was clicked, and it is able to shout its message. So let's just log the message. Let's log the message, and we are shouting to the channel called actions. So log needs a storage of some kind. It can be a so-called cell, or it can be inside the log node itself, and that's the simple variant. Again, we're going to use an empty dictionary for this. When I click the button, you can see that we get increment. So the button is shouting on this channel, hey, I'm being clicked, the message is increment. Now another variant of a button is the variant with as. Now the variant with as allows to overwrite this message. So instead of sort of shouting whatever the button's caption is, you can shout something else. For instance, you know, in case of increment, that's going to be 1, so the step or the delta that we want to sort of increment by. Now again you can see the caption is unchanged, but when I press this button we get 1 instead of an increment. Let me just fill it a little bit. So let's rename this actions thing to deltas, because that makes more sense. And let's rename this here. So now again nothing changed. So let's add another button. We can do this by using "-v", which is like a duplicate command. Let's change this to decrement. So this is going to be our decrement button. We're going to use -1 as the delta. And now if I click the decrement button, you can see we get decrement. If I click increment, we get increment. Very nice. Let's organize these things in a row so that they are lined up sort of horizontally. So we can use raw node, which is purely a visual node. It has no logical sort of component. Then we will move the button into the row. Now a row expects 2 or more elements inside of it, and you can see that the row disappeared. Now we have 2 buttons lined up. Let's use gap to add a gap of 1 between the buttons, and that's how it looks now. And the buttons are still perfectly functional. Now the next thing, of course, that we would like to do is we would like to have the count. And this is sort of where progress in terms of UI stops, because we are in a terminal, and this means that we cannot do like a nice big count or something like that. Right now we need to just use code for that. So, or I mean, it's not code, but like, you know what I mean, I guess. So let's have a cell. So a cell is a special node that stores a term inside itself, and it outputs a so-called const signal. So we in Wirewright we have 2 different signals. We have a const signal and we have a pulse signal. Now a pulse signal is like a shout. You shout and the shout goes and the shout disappears at some point. And so in the future this shout will not be heard. So because it disappeared after some time, like it dissolves, dissipates, I don't know what's the right word. So const signal on the other hand is maintained. So we use pulses to sort of do notifications, to do user actions. Whenever I press a button, for instance, that emits a pulse signal. So it is something ephemeral. It's something that will disappear almost immediately. And if you have a node that was not in the system, that was not in the program, and you've done some action, and then after that action the node appears, and this node is interested in that action, well, the action will be lost. So yeah, because it's too late. The node is arriving too late. It's arriving too much after the action was emitted, so to speak. And maybe I'm not explaining this the best way, but I guess it will do for now. This needs a lot of writing if properly explained. So if you want to explain properly, so let's just initialize this count here. So now this cell outputs 0 on the edge count, so it's sort of constant there. Now we need to somehow read this count and add our delta to it. So how do we do that? Well, transform nodes come to our help. So a transform node, as you can see right here, transforms incoming pulse into outgoing pulse using something called nitrine, which is like a little embedded programming language that is very tightly coupled to Wirewright and to everything. It's a term rewriting system, so to speak, or like it's a language that is very close to that in spirit, very close to term rewriting. So again, everything that you see here, or at least like everything in nitrine, is purely functional, and all the effects that you will see, all the mutations that you will see, are done by Soma, so by the sort of outside world. What you see right here, this program that I'm writing, even the cursor that I'm moving, these are all immutable, persistent things. So right now, again, it's all in development, but in the future we will have sort of a full history of programs. Like as you edit them, of course, in such a setting, it is very hard to sort of discern user events from program events because of what I'm going to show later. But this is a very hard topic, so to speak. So, our choice instead is to store everything. And since we are using efficient, right now they are not very efficient, but it will be sort of efficient at some point. There's nothing preventing us from making it efficient, right? Sort of storage efficient ways of sort of storing the entire history of the program from its very beginning to the current state with branches and so on. So we are able to do that. We are able to do, or we will be able to do that. We will be able to do the navigation and so on and so forth in this history. But let's just continue with the count, right? So transform nodes basically convert what I was talking about as shouts into other shouts using Nitrine. Again, Nitrine is this little language that is used for transformations. So let's just take a look. So we will have deltas. We'll have deltas, and we will convert deltas to counts. Now, as you can see, we have two variants of transform available. One is that does not take state, and one that does. And we do need state here. So we'll use with, and then we will use state. So what's our state? Our state is count. So now in this sort of body of the transform, we are writing Nitrine. So let's just write some Nitrine. So what we are going to do is we're going to do count plus underscore. Now, right now, that's not like the most readable thing ever. But underscore means basically the incoming signal. So the signal incoming into the transform. So basically, whatever is shouted into deltas is bound to underscore in the body of the program. And the state is called the same as the edge in the majority of sort of cases. Now, yeah, ideally in the future we would like to be able to do this, but this is right now not important. This is not important for progress. So, okay, what does that do? Well, let's check it out. So I'm going to change this to counts, and now if I press increment, you can see that we get the same stuff. Well, that's because our count is 0. So let's try to initialize our count to, let's say, 100. And let's try to press increment. So you can see that we get 101, and if we decrement, we get 99. So we are sort of halfway through. So let's try to take a look at those. So we will need latest at counts at count. And what this does is it basically captures the latest thing that we have shouted, so to speak, at counts, and then it stores it in count. So latest node is able to talk to the cell node and to convince it, so to speak, to change its value to whatever value was shouted on counts last. So now we will see that our counter is working, and you can see that we get our nice increment and decrement functionality. So similarly, again, it's quite a canonical example for me personally, but we can try to add, for instance, a reset button. Now that's a little bit of a spoiler. Reset to, or let's do as 0. Now we are not going to send it to deltas, we are going to send it directly to counts, as 0 to counts. And then we'll add an empty mailbox for the button. So now if I hit reset, it will reset to 0. Very nice, very nice. Okay, so this is all very nice, but like what's interesting about Wirewright, like one interesting node that I think is worth showing, or like one interesting thing that is worth showing, I guess, is the ability of a program to edit itself. So we need to be able to, something that is emergent, so to speak, is very sort of curious and interesting thing is multiple cursors. So one way I can do that is I can type a cursor. In fact, if I hit escape, this is kind of a bug, but not really, it's just not implemented. So if I hit escape, you'll see that what we are, again, as I have described, we are this player character in this world where cells exist and transforms exist and logs exist and so on. And we are a player character in this world. And so we are this cursor, this object, so to speak. So what if we type, so again, this is a special form of a cursor, but let me just show. What if we type another cursor? Well, let's try it out. So a cursor under the hood looks like this. So it has the left hand side, it has the right hand side. So again, if I type something and I move left, so what is before the cursor is stored in this left hand side, and what is after the cursor is stored in this right hand side. Now, I don't think that would work though, no. So regardless. The next thing that the cursor has is a mailbox. Similarly to a button, Soma needs to communicate with the cursor regarding what keys you've typed and so on. The cursor also needs something called a broadcast edge, which is similar to a normal edge, or as I've called it, for the analogy's sake, a channel. So to speak, these broadcast edges are special channels for cursors in that analogy, where we can shout and only cursors will hear us. Well, that's, of course, that has nuance, but regardless. So let's just create. Soma only cares about cursors which have the user broadcast edge. So now, witness the magic. You can see that now I have two cursors and I can type. Now, if I hit backspace now, you can see that one of the cursors destroyed the other one. So basically the one below there destroyed the first one. So the first one did not have anywhere to go, so it just did nothing, I guess. And the second one is has destroyed this cursor because it's like it's invaded, so to speak, the first cursor. And so you can see that it's frozen sort of mid-air while it was executed. So you can witness here how Soma communicates with the cursor. So it sends it, for instance, key backspace. So whenever I press backspace, it sort of sends this signal here. I'm not sure where that cursor has gone, but regardless, I think what happened is, oh yes, so what happened is I put the cursor inside the mailbox. The cursor consumed, like the outer cursor consumed the key backspace that was in there just a moment before. Since it doesn't have anything to do, it did nothing. Then it consumed the other cursor, and it does nothing in this case because it doesn't know what to do with a cursor inside of itself. So things like these happen. Let's put it that way. Just don't do that too much. Okay, so this was a user-controlled cursor. What about a cursor that the program can control? Well, let's try that out. Instead of giving it the user edge, we will give it the we'll give it some other name. Let's do foo or something like that, or like my cursor, right? And then let's try to actually do something. I don't remember how though, so let's just take a look. I think it's edit cast. Yes, converts pull signal to root-centric edit broadcast. That sounds like too hard, but regardless. So let's do my cursor commands to my cursor. Let's create a button that says, for instance, move. Now that's not what I wanted to do. Let's just create a button that says move up, and as its message it's going to send key up and to my cursor commands. And then let's create another button, and this button is going to send key down, it's going to send that also to my cursor commands. Now if I hit move up, nothing happens, but if I hit move down, you can see the cursor moves down. Very nice, right? So obviously we can sort of automate this. We can do all sorts of fancy things with this, and one of the more interesting things that we can do is we can actually create a group, and instead of moving the cursor up and down, we can move the group up and down using this time not this, I think it's control left or something like that, I don't remember, I think it's control up. Let's try that out now. The editing shortcuts are not like too good right now, but regardless, so let's try that. Yeah, so you can see we've got move up with the group now, and if I put my cursor in there, you can see that it moves with the cursor and so on. So this is very nice, so we can have this kind of motility within the program. What then? So there are also nodes that allow us to look around, for example. So let's use the look around node. Look around. It takes a snapshots edge and a capture edge. Then we'll create a button. Let's do capture. It's going to go to capture. Capture doesn't care, or look around in this case doesn't care what it receives on the edge capture, as long as it's something. So, and then we will log. Now this is probably going to explode, I mean in terms of size. So let's do snapshot here, and then like so. And this obviously should be plural, because as a convention we call our things snapshots, call our things plural when they are pulse, and we call them singular when they are singular. So if I hit capture right now, as I have said, this creates a lot of noise, but you can see that it has managed to capture a lot of things, by the way, that you shouldn't be able to see, but that's like a more of a bug. But you can see that it captured the program around itself and before itself. This is very interesting, right? So one of the things that we can do is we can try to actually store it inside of a cell using latest. So instead of using log, which as you can see is quite noisy, and you can see like we are outputting before and after here, so let's just output before because we don't have anything before, so it's going to be less noisy. So what I'm going to do is I'm going to do latest. I don't remember, I think yes, this will work. So we'll output latest snapshot at snapshots, and we will only take the behind part and we'll leave the ahead part. And then I'm going to output the cell, which is going to be, let's say, behind, and then I'm going to output the template, which is going to be just behind. Now let me use one of those fancy key bindings like so, and then let's just have a cell here at behind. So now if I press capture, you can see there is nothing, but if I move my cursor here, let's say type hello, if I capture, you can see the cursor is there. Now what if we capture this sort of automatically? Well, that is possible, so let's try to do that, I guess. It would be really nice if it worked, but it wouldn't at the moment. Let me see what we can do about that. Now that is very suspicious. What is it doing? Yeah. So yeah, this is like fanciness, right? So, you know, one of those cursors broke out, which is really sad. So yeah, these things are severely under designed, so to speak. So yeah, but this is supposed to work, right? Yeah. Now it would be nice again if this worked, but it doesn't for some reason. Now let me see at behind. Yeah. So let's just take a look. Oh yeah, I know why, So basically cells don't like when they have cursors and they disable themselves. And so this is probably a bug. But I don't know. Again, these things are fairly complex and it's hard to think about them. So regardless, let's just take a look. So let's say we have a cell, or I mean, I don't know, so something like a log does not care whether it contains a cursor or not, so we can use that just for a demo. Let's just take a look here. I mean, it doesn't matter though, but sure. So, well, yeah, so then we would not need this whole latest thing, so let me just remove it. Let's have a log of snapshots. In this, limit is going to be 1. So it's only going to be 1 snapshot. So if I hit capture, you can see that we've got this weirdness, obviously. So let's do transform snapshots behind, and then, my gosh, what is this doing? Behind, ahead. We're gonna skip now to behind. And so here what we'll do is we'll output behinds. Now if I capture, you can see that we've got only the thing there. Okay, only the thing there. Now apparently limit does not work in a log, which is a very weird situation to be in. But yeah, it's supposed to work, but apparently it does not. Interested? Okay. Yeah, it doesn't work. Well, that's sad, I suppose. Let me just remove this guy so it doesn't clutter everything. Yeah. Let's try limit 3 and see if that works, because it's probably like a range issue here. Well, yeah, you can see 3 works. Well, let's keep it with 3. Now we are going to do periodic. Like, we can press the button here, we can also emit a periodic signal, but this is like a hack. It will be removed, this node will be removed because it is wrong. So we need to emit an event pulse at behind, or I mean at capture. Let's just emit true here, something like that. And now what we can see here is that the program is able to observe itself being edited and perhaps even react to that, but that's not sure. So the important thing is that we can now look around and observe things. So what can we do with this? Well, we can do anything with this. For example, we can, oh, I don't know, we can do movement using our, so you can see my fan is starting to spin due to this periodic thing because it is emitting very fast. So let's transform behinds period underscore star, or it's gonna be another way. like so, to let's say my cursor commands key C up. What would that do? Well, let's check it out. I'm going to move the cursor. I guess there is no easy way to do that because we are in the terminal. Good, so now we have this, and if we do this and hit capture, you can see our look around moves like so. So this is just one of the examples. We have a more complex example there somewhere. If I open examples, eat and bounds it's called, you can see that this is a more sort of complex program that is able to move. Now that is not supposed to happen, but regardless. So you can see this is like a bigger program that is able to move and so on. Again, that is not supposed to happen. This is all termbox fault. But yeah, so you can see that we are doing this sort of more in a more complex manner, with some state, with a feedback loop, with handling of different stimuli, and so on. So yeah, this is just a short demo. Again, there's not much done yet, but it's already looking pretty interesting, I would say, especially in the development experience. So yeah, that's that.